So my thought would be to start first with some math problems. So this is test 12. We're on sections 10.1 through 10.4. I did put a problem set up, but I told you it's not going to be graded or not going to be turned in. So you can do it tonight if you want as practice. I could even put the solution up if somebody sends me an email to remind me at some point today. I could probably do that third period actually. But I could put the solution up for it as well, just so you can check your work as you're going through it. Okay, but I recommend never read a solution. Do it first. Reading a solution is very misleading, especially in math and science. It's very misleading. Anyone can read a solution and think they understand something. And then when they have to go do it later on their own, it's a very different ballgame. Okay, so again, if I put the solution up, don't just read the solution. Do the work, then check the solution. So this whole topic again, heat transfer, that's the math that we're concerned with. Some facts that we should write down first, and I'll give you things. C is called specific heat capacity. And that variable really has to do with how much heat you can take on, or an object can take on, before changing temperature, or as you change temperature. So, for example, we've used water as an example that has a higher specific heat capacity. That means that it would need more heat to change by the same temperature as metal would. The human body has a specific heat capacity. Certain food, or anything literally has specific heat capacity. It's a change of temperature as a function of time and heat that's input. But C is that material property. You'll be given a table or you'll be given values, right? One of those two things. A table or values in the problem itself. What else should we know? M is mass, as always. L is the latent heat. Now, it could be of vaporization or of fusion. Remember that we have two options here. We've got LV and LF. This is for when we're going, LV is for vaporization, so from a liquid to a gas or back and forth. And F is for fusion, that's from a solid to a liquid or vice versa. Okay, LV and LF, vaporization, fusion, vaporization, fusion. Whenever we use ML, we notice there's no delta T. No delta T in that formula. Why is there only L? What's happening at the moment when we use L?
Temperature doesn't change.
Good. The temperature doesn't change. What does change, Brandon? What are we trying to focus on with those parts?
The phase.
The phase, the state of matter. It's going from liquid to gas, from solid to liquid. Okay, it's the phase that's changing, so there's no delta T in that formula. So let's jot down the two formulas on the left side now that relate to these. So for C, we're talking about Q equals MC delta T. And for L, we're talking about Q equals ML. Now, yes, there are other formulas, the conversions of temperatures. I'm not going to spend today going over how to convert Fahrenheit to Celsius. You should have practiced it. We did it in class. It's just plug and chug those problems. You plug in the Fahrenheit temperature, you get out the Celsius. You plug in the Celsius, you get out the Fahrenheit. You'll have the formulas on your formula sheet. So at that point, there's no practice needed for that. You get what I'm saying there? Okay, it's just plug and chug. You plug it in, you get an answer. This is a little bit more difficult, obviously, so I'm going into this idea. Now, there's one other thing we spoke about with this, and we talked about calories and what they are. Something that you probably want to know. It's showing up on a couple of your homeworks you've noticed by now. 1 calorie is 40. You got it?
Oh, 0.4186.
Yeah, 4186 joules.
I thought it was 1 kcal. Oh, the capital C.
Yeah, very good. A kilocalorie or a capital C calorie, which is the word we use all the time. We don't use that lowercase c calorie anymore. Anybody. It was old chemistry and physics back in like the 1600s. Nobody used that anymore. Capital C calorie is the unit of measurement we use. And it's because it's a much bigger unit of measurement. Okay? And that's what we think about for dietary needs, right? For energy use. So that's a good conversion factor to have. You don't have this memorized. You do not. I would give it to you on the test. But you do need to be able to convert from one to the other. So if you solve for an answer in joules and I say, well, how many calories actually is that? Okay, if I have an answer of like 20,000 joules, I can multiply by my conversion factor. Remember using dimensional analysis? We'll do an example of that when we go through this. okay, of dimensional analysis. Just conversion of units is what I'm saying there. So let's take a look at, I don't know, I'm going to give an example, a template for one that you might consider. So let's say the following. Let's say that, this is kind of like your problem set problems that have been asked. Let's say that in the process of working out, you expend 300,000 joules. Okay, in the process of, I'm not going to write all this. Let's just leave it. In the process of working out, you use or give off or expend 300,000 joules. If your body temperature, God bless you, if your body temperature goes up by 5 degrees Celsius, and your mass is 80 kilograms, determine your specific heat capacity, your personal specific heat capacity. So again, in the process of working out, you use up 300,000 joules. Your body temperature goes up by 5 degrees Celsius. Your mass is 80 kilograms. Determine your personal specific heat capacity. If you expend 300,000 joules, what variable is that? What variable in this chapter is joules, or does joules go under? What variable? Q. So that's the energy that you use, gain, lose. In this case, you're gaining some energy by doing this. Right, you're working out, your body's literally heating up, it's gaining energy. Now you're doing work also, so you're expending energy at the same time. But let's say that's the energy change of your body. We know that your mass is 80 kilograms. And we're told that we're trying to figure out your personal specific heat capacity. How about the temperature piece? Who can tell me what to write down for that? What do you think? Well, what is 5 degrees Celsius?
Delta T.
So what's the
Delta T.
Delta T. Very good. It's not TI. It's not TF. It's the change in your body temperature is 5 degrees Celsius. So we did examples in class where I gave you the initial temperature of the copper in the water and you found out the final temperature, TF. Or you did examples in problem sets where you might have to find out the initial temperature or final temperature. This kind of a problem, I'm giving you the change in temperature. You could also find the change in temperature, delta T, as a variable. If I gave you C instead, and said find out how much your temperature, body temperature goes up by, you'd be just searching for delta T. And that's in your formula. So let's go ahead and use our formula now. So there's no use for me to write TF minus TI in this formula because delta T itself is a given value. So we should solve this formula for C to get our specific heat capacity. So how would I rearrange this formula to get C by itself? Kev?
C equals Q over M times temperature.
Yeah, let's move the M delta T down to the bottom to get C by itself in this problem. Because we're trying to figure out our specific heat capacity. And at this point, let's go ahead and just plug in. The amount of energy change is 300,000 joules. Our mass is 80 kilograms. And our body temperature goes up by 5 degrees Celsius. What do we get? 300,000 over 400. What does that become? 750? And my units are a little bit funky, but I can tell what my units are. My units of C are right here, guys. Joules per kilogram degrees Celsius. Joules per kilogram degrees Celsius. The units of C are embedded in the formula. But human, okay? Specific heat capacity of a given human being. 750. So I want you guys to recognize that although we haven't done every possible problem, you should be able to, as we always say, manipulate. change the problem to figure out what you're actually searching for. Okay, what you're searching for. How many calories would you have burned in this process? Who can tell me how to figure out how many calories we would have burned in this process? What do you think, Helen?
So 150 multiplied by. Oh, but how many calories?
Calories, I want to know.
Divide by.
Careful. It's not 750. It has nothing to do with 750.
300,000 divided by 4,000.
So 300,000 is your number of joules, right? And we want this to become calories. So here we go. Here's our conversion. 1 calorie is 4,186 joules. So let's just perform that operation on the right side of the screen. 300,000 times 1 over 4186. Pretty much divided by 4186, right? Just divide it. My joules cancel out as units. Joules cancel with joules. 300 grand over 4186. How many calories does it turn out to be? What is that? 71.6 calories. Pretty reasonable amount. And these are just arbitrary numbers I chose right now. They happen to work out. It's 71 calories. Think about working out, right? When you work out, every like 10 minutes on a run, you burn about 100 calories. It's a good number to have. 100 to 125 in a 10-minute run. What else can I ask you? I could also ask you about calorimetry with 2 items, right? That was just heat. And that was heat of something, or the heat of something that is being either added or taken away from a human body or an object. But what about if we have 2 substances now? Where did the 2 substance problem come up? It came up with like some sort of a solution of liquid with a solid submerged in it, right? That was the really main thing we've talked about. Or we could talk about hot and cold water, or ice and water. We could do that as well. So let's say the following. Oh, I got a good one actually. Let's do this. Let's say that you put ice into water. Instead of a metal, it's just ice and water. It doesn't matter what it is. It could be a metal in water, it could be a metal in another fluid or liquid. Let's say that you drop a couple ice cubes. Let's say the mass of those ice cubes is about 1/4 kilo. So you drop a couple ice cubes in a glass of water. And the water is a little bit more massive. Let's say we have around 0.75 kilograms of water. Drop a couple ice cubes in there, and then you wait to figure out the temperature it gets to. Okay, let's say that the ice cubes had a starting temperature. Oops, that's the water. Ice cubes have a starting temperature of, it's got to be something below 0, right? Or 0 or less. So I'm going to say -4 degrees Celsius. And let's say that the water was at room temperature, 20 degrees Celsius. So again, we've got ice, frozen, water in the liquid form. We know the masses of each. And I simply want you to figure out the final temperature that they get to, the equilibrium temperature that they reach. Equilibrium temperature that they reach. Or you know what? We did that in class, right? The equilibrium temperature problem. Let's make it a little bit different. I have an idea. What about this? I just want to vary it up so you have multiple examples to study from. Let's say that the initial temperature of the ice is unknown. Okay? But after a little while, these 2 items come to equilibrium. And they come to equilibrium at a temperature of, I'm going to say, 18 degrees Celsius. Okay? They come to equilibrium at a temperature of 18 degrees Celsius. So notice what I wrote down right away. If they come to equilibrium at that temperature, it means equilibrium occurs at the end, after things have melted, after things have cooled off, right? So that's the final temperature of both. Remember, the equilibrium temperature of 2 items means that they have to be the same. Equilibrium for thermal systems is the temperature is the same. So this is always going to be the same when it reaches equilibrium. I told you that it reaches equilibrium at 18 degrees Celsius, so it'll get to that point. But we want to figure out what temperature the ice was to start. How cold was that ice to make this drop 2 degrees Celsius and chill down the water? Okay? Now, what do we know? What do we need? What else? And we have it, but we just don't have it written down yet.
Specific heat.
Yeah. And where do we find it? In a table, in the problem, somewhere. So water has a specific heat of 4.186 times 10 to the third. Notice? Any familiarity with this number?
1.186.
Calories.
This is the same conversion as calories, right? 10 to the third, you move it over 3 spots. It's 4186. So the specific heat capacity of water is not a coincidence that it's the same number of calories. Calories are based off of this idea. It's just a fun fact. Now, the specific heat capacity, though, of ice is different. It is not 4186. Anyone know it, or I can look it up? I have it right here somewhere. Yeah, I have it on my notes. Ice is 2.09 times 10 to the third. And again, this is joules per kilogram degrees Celsius. Joules per kilogram degrees Celsius. Those are my units for C. It'll be given to you in the table, so you don't have to even know what the units are, right? If I give you a table, if I give you a value, it'll say that number. So let's go ahead and go through this process. What's the key to everything here? Conservation of energy. The whole key is conservation of energy. That allows me to say that whatever Q1 loses plus whatever Q2 gains, we have to net out 0. That's the key to all these problems. Any calorimetry problem, when there's heat loss from one item and heat gained by the other item, they must balance each other out. Okay, the loss of heat from the water goes into the ice. That's another thing we need to know. Heat always transfers from hot to cold. Always hot to cold. All right, so let's take a look at the math now. So I'm going to move Q2 over by putting negative Q2 on the right side, and that's fine, I can do that. Remember that negative sign will end up dropping off because one of our temperatures will go up and the other temperature will go down. So our delta T will be negative on one side of the equation and it'll be positive on the other. The negative delta T will cancel with that negative in front of Q2. What's my formula for Q when it comes to temperature change? Again, temperature change here. Oh, shoot. The ice is also changing phase, right? Right? The ice is melting. Okay, so we'll figure that out. I got you. All right. So this is the ice. This is the water. The water is going to lose energy via change of temperature. The ice will change temperature. Screw that up by putting ice in there. Here. Simple. Okay. Let's say the ice doesn't actually melt. Let's say the ice gets to a temperature of negative 2 degrees Celsius. They don't reach equilibrium. Okay, so the problem is the ice is dropped into the water, it starts to warm up the ice, and the ice gets to negative 2 degrees Celsius when the water drops to 18 degrees Celsius. What was the starting temperature of the ice? I'm doing this on purpose because if I include a problem where there's also a phase change, then I have to truncate my temperature, I have to add the ml, and we're going to do that kind of problem in a minute, but not with the calorimetry where it's happening. Okay, where it's just one item happening. So let's take a look at this now. It's going to only negative 2 for the ice. They're not reaching thermal equilibrium here. Sure, some energy is going from the water into the ice, but not enough to melt it completely. Okay, just to warm up the ice a little bit. So as a result, let's take a look at what we've got here. We've got God bless you, MC delta T equals MC delta T. I can plug in what I know. I've got 0.25 kilograms there. I've got 2.09 times 10 to the third. Delta T is going to be final minus initial, and initial is unknown. And then on the right-hand side, I've got everything also. The mass of the water, the specific heat capacity of water, and then the final minus initial temperature over here will be 18 minus 20. Okay, so the calorimetry temperature problems, I want you to recognize that if we're looking at two items, I'm not going to have a phase change for those two items. And that's why I changed and altered this problem, so that this only went to -2 degrees Celsius. So our goal is going to be to figure out what was the temperature of the ice initially, and that's right here. So this just becomes plug and chug. Subtract these two, negate this with a negative, those will cancel, multiply throughout, multiply these. You could divide by this, or you could distribute it to both of those terms. Whichever way you want to do it, it's 6 1/2 dozen. And it does not matter which way you do it. It's okay. So 1/4 of that coefficient there, and then distribute that coefficient. So 1/4 of this number should be around 0.5 or so. So that's going to be 0.5025. What do we get when we multiply this? Can I get some help with the calculator, please? Let's multiply these two values together. Let's multiply these three, or let's multiply on this side as well. This is not distribution on the right side though, right? We just multiply three values together. Give me a number on each side, please. Thanks, Darren.
522.5.
On the left? Thank you. Parentheses -2 still, right? Minus T1I. $3,139.5. The negative should cancel, right? Because we have a negative here also. And that's a negative there. But that's the numbers, right?
Oh, okay. I didn't do that.
Yeah, no problem. Now, this is what I was pointing out here. At this moment in time, you can do two things. Either you can distribute the 522 to both of these. You can distribute the 522 to both and solve. Or you can just divide by 522.5 on both sides. I would recommend dividing by 522.5 on both sides. I think that is the better route to take. What do you got?
The number on the right side is wrong. I messed up.
Okay, what do you got?
It's 6,279.
6279?
Yeah.
Thank you, sir. And can you tell me, because you forgot to multiply by 2. Got it. Can you tell me what you get when you divide that number by 522.5? We're going to get rid of this coefficient by dividing by 522.5.
12.02.
Nice. So that's my temperature change. We can see that already. So let's see what the initial temperature was then. So I don't need parentheses anymore. I'm going to get rid of them so I remind myself that it's really not parentheses I'm worried about anymore. And what am I going to do with the 2? I can add the 2 over. I add that over, I get 14.02. But that means TI is negative 14.02. God bless. God bless. So the ice was at negative 14 and it warmed up to negative 2. That's what this problem is getting at. So again, conceptually, why did the water only lose 2 degrees while the ice gained almost 12 degrees, right? Here's the gain of the ice right here. That's how much the ice gained, right? This is delta T from the ice, change in temperature. So the ice gained 12 degrees, but the water only lost 2. How? More, how is that possible?
The water is more massive.
Water is more massive, triple massive, right?
And pretty sure we already said this before, but the water was like temperature was different, or yeah, so it was like more
Specific heat.
Yeah.
The mass is right, Lord. It's the specific heat. The specific heat capacity of water is far greater. 4186 versus 209. Okay? 4186 versus 209. So, and that's a good question you could expect for me to ask. Like, explain the logic behind why one of the temperature gains was not equal to the other temperature loss. It's that heat that one loses, the other gains, not the temperature. Unless they're identical materials with the same mass and the same C value, if it's the same specific heat capacity and the same mass, then my temperature gain is equal to your temperature loss. But that's not the scenario in this problem. That's not the case here. Okay? questions on this idea of calorimetry? Okay, one more to do, one more math type problem. We covered 3 problems, right? We talked about where we can have the temperature change only, we can have calorimetry, and now this last problem we're going to have phase changes involved. Phase changes. So we have the temperature change at the beginning with the person working out. We had the calorimetry where you have a temperature change of 2 items. And now let's take a look at one item that can change temperature and or phase. Either one of them. So give me a substance that is on our table. So we got options of options are not many options actually. You need the C values for both of these, huh? Our options are water, lead, and aluminum. Lead. All right. So the substance is lead. And it turns out that we have lead. We have lead at a temperature of 30 degrees Celsius. We're going to keep adding heat to it until it reaches 450 degrees Celsius. We're going to keep adding heat to it until it reaches 450 degrees Celsius. Okay? Now, let's say the amount of heat that we add to it is 2 million joules. Determine the mass of the piece of lead. Now, we need some facts, right? We need some key facts, some numbers. What numbers do we need to actually go through this problem to figure out what's happening? What values do we need to look up in a table for sure? Joe, give me something.
Specific heat of lead.
All right, so we need that for sure. And that is going to be 100 or 1.28 times 10 to the second. Agreed. Good, Joe. Good. What else do we need? Kim.
We need to know like when the phase change occurs at the melting point or the freezing point.
Good. So we need to know the melting/freezing point. And the boiling/condensing point. The melting point of lead is 327.3. The boiling point of lead is 1745 degrees C. From that information alone, what can we deduce? What can we deduce from that information alone? What? I'm saying from this information alone, right here. There? Right?
It's frozen.
What do you mean it's frozen?
Sorry, it's below the freezing point. So.
At the start.
Oh
Okay.
yeah. Sorry.
Joe?
It's going to go from a solid to liquid.
It's going to go from solid to a liquid. It's a solid when it's at 30 because it's below the freezing point. It's a liquid when it's at 450 because 450 is above the freezing point or the melting point. So if I go from 30 to 450, which of these do I pass is the question. I pass 327, right?
Yeah, but I don't understand how is that the melting and the freezing point?
Because think about it. If I wanted to melt ice, I need to get it up to 0 degrees. But if I want to freeze water, I have to get it down to 0 degrees. There's a certain temperature where a solid starts to become a liquid if you keep adding heat. Then there's the same temperature that a liquid becomes a solid if you remove heat. So the temperature that ice freezes or ice melts is 0 degrees in both cases.
So lead will freeze and melt at 300.
One or the other. It depends on what we start at. If we start below this temperature, it means that it starts below the point of which it would melt. And before you melt, you're a solid, right? Like if I'm the ice right now, and I haven't reached the melting point for ice, I'm a solid. And then when I reach the melting point for ice, I melt into a liquid. Agreed?
Yeah.
So right now, the temperature of lead is lower than this number. And since this is the melting freezing point, this is where the solid liquid boundary comes into play. So if we're lower than the solid liquid boundary, we're a solid because we're cold enough. It's like ice. Use ice in your mind.
Okay.
And then if we get to a temperature greater than this, which we do, we get up to 450, it means that we've passed this mark and we've started to melt. If the temperature went instead from a higher to a lower, you wouldn't be melting, instead you would be freezing. If you start as water, all we need to know is whether we're passing this point or if we're passing this point. And clearly we're not going anywhere near the boiling point of lead. So I just want to make sure that we recognize that, yes, we have these two values, but for this problem, this one doesn't give us any information because we're never crossing 1745 Celsius. So based on your temperature change, figure out which of these you're crossing so that you know what kind of a phase change is occurring.
So it's melting, right?
Precisely. So this problem, it could have been melting, it could have been freezing, it could have been boiling, it could have been condensing. Freezing and condensing only occur when you go from a higher temperature to a lower. But melting and boiling occur when you heat things up. Okay? So we know that we've crossed the melting point, and when things melt, we need the latent heat value. We need the latent heat value. That variable, if you recall, is L. Now, am I looking at LF or LV? What was the difference? Why did you say F, Aaron? When things are freezing or melting, just look at the letter F in freezing. Think of LF. It's really called fusion, as Darren said. But think of F for freezing. And think of boiling as evaporating, and that's vaporization. So remember, for this one, we always use LF. For this one, we use LV. So in our problem right now, we are concerned with LF. See what I'm getting at there? That follows along with the same concept. So LV is very useful only if we're boiling or if we're condensing. That's when we use LV. But we're not, so we're not going to use LV. The LF value, the latent heat of fusion for lead, again, right in the table. You have to be able to use your tables out of your notes. 2.45 times 10 to the 4. And remember, the units of L are different than the units of C, but you don't have to memorize them. They're also in the table. So either I'm going to give you the value, or I'm going to say to you, you know what? Find the value of C. Find the value of LF. In this problem, I'm not having you find C. We found C of a human body earlier, right? The specific heat capacity. So this one, I'm going to figure out the actual mass. Before you go, give me another 2 seconds, right? Let me just write it down the last part here. So we've got Q equals Q1 plus Q2 plus Q3. I know there's 3 Qs because it's going to gain temperature. So this is going to be MC delta T. It's then going to melt. So this is going to be ML. And then it's going to gain more temperature. Recognize that the mass is the same for all parts. The mass is not changing. So the mass could all just be called M instead of subscripts for the mass. So this is the problem in itself right here. The total Q goes in here. You have all these values for C's. You can look up the C value for lead. It's the same in either phase. The C value doesn't change. Your goal is to find M. My recommendation, factor M out. Factor it out. Have a good day.